Alright, welcome back. We're doing section 3.2. Section 3.1 was about the definition of rings and all the different kinds of rings you can have. Commutative rings, ring with identity, commutative ring with identity, integral domains and fields, and all the different properties they have. So on this particular concept here, we're going to dive into the basic properties of rings and really start to the idea of proving when you happen to have rings and stuff. So we'll start off in section 3.2 with Theorem 3.3, which says this: let R be a ring and let A be an element of R. Then the equation A plus X equals 0 in R has a unique solution. We're going to go back and look at those basic definitions of what it means to be a ring and analyze certain aspects of the properties and stuff. So let's take a look at this idea of A plus X equals 0 in R. Now, what this theorem is telling us is the solution for this equation has a unique solution. That idea of proving uniqueness. Traditionally, how you prove uniqueness is you assume there are two of them, and then you show that they're equal to each other, and then basically you've only got one. So, for this one, again, we're going to assume it's not unique. Assume that the solution to the equation to A plus X equals 0 in R has two solutions. It's not unique, is basically what I'm after. Assume there's two solutions. So let U and V be elements of R such that U and V are solutions to the equation A plus X equals 0 in R. This implies that A plus U is equal to 0 in R, and A plus V is equal to 0 in R. So as, we'll start off with V. V is equal to 0 in R plus V. Statement of reason here. This is pretty much by the property of the additive identity 0. Okay. Additive identity. Then I'm working the equation, so I'm kind of indenting this a little bit here. Then V is equal to A plus U plus V by substitution. I replace 0 on R with A plus U. Hence, V is equal to U plus A plus V. And what did I do there? I dropped the parentheses, and I, instead of writing it as U plus A, I did A plus U. So instead of A plus U, I wrote it as U plus A. So I actually did two operations here, and this is, as we shorten this thing up a little bit legal here, I wouldn't do more than two. You can end up losing your audience when you're doing your proofs here. This is by associativity, because I moved the parentheses, and commutativity. Associative and commutative properties there. Thus, V is equal to U plus A plus V by associativity again. I put some more parentheses in there. And the reason why is I want to emphasize the u plus a, because as a plus u and u plus a are the same thing, that's equal to 0 in R. This gives us v is equal to, excuse me, I want to put the parentheses in the wrong spot here. This is the u, put the parentheses here, the a plus v. Sorry, put the parentheses there. Because the a plus v is your 0, a plus v is 0, so it gives you u plus 0 in R by substitution. Hence, v is equal to u. And when you add 0, you pretty much get the element back again. So, put the parentheses in the right spot over here. The a plus v, that replaces with 0. You end up getting v equals u. Therefore, put in English, the solution to the equation a plus x equals 0 in R is unique. That's what we're after. There's only one solution to this particular equation. Now, because there's only one, we're going to give it a special notation. What we're really trying to do with this is actually introduce the concept of negative. I mean, look at this thing. I've got a plus x equals 0 in R. You want to solve for x, you want to pretty much subtract a from both sides, but we haven't defined subtraction in the concept of rings until now. So, therefore, and just to let you guys know, 3 dots in a little triangular fashion is mathematical symbols for therefore, as a plus x equals 0 in R has a unique solution, then we will denote this negative a as the unique solution. So, this negative a is what we're going to be calling this guy. We're going to introduce the negative. And when introducing negative, you're also going to be introducing the concept of subtraction. So with that being said, this also means that we will define subtraction. So b minus a means that a plus, or b plus negative a, which is the same thing, equals negative a plus b. So if we got b minus a, you should think of that as meaning b plus the additive inverse of a, then b plus negative a. And remember, with rings you have commutativity, so you can write this as b plus negative a, or that's the same thing as negative a plus b. So subtraction is adding the additive inverse of the element. But you kind of have to be careful with this, because you think about negative 2 or whatever the case may be, and you're familiar with that in terms of the world of integers. But if we go into a different world, like for example in Z6, so I put this equation up here. I want you to solve equivalence class 2 plus x equals equivalence class 0. Well, if I did that, equivalence class 2 plus x equals equivalence class 0, I'm going to solve for x by adding the additive inverse of both sides. The additive inverse of the equivalence class 2 would be equivalence class negative 2, or subtract equivalence class 2 from both sides. This cancels, so x is equal to, and 0 minus 2 would be negative 2, but this is in Z6. And just to remind you, in Z6, the elements that you're allowed to have, because this is a finite ring in Z6, is 0 through 5. 0, 1, 2, 3, 4, and 5. These are the only elements you're allowed to have. And x in equivalence class negative 2 is not in here. So in Z6, you've got to put it back inside the set. So even though this is the quote negative element here, you got to make sure he's written the right way for the whatever ring you're having to play with. Therefore, x is going to be equal to negative 2 is going to be equivalent to, if you just add 6 to it, equivalence class 4. So actually, equivalence class 4 is the additive inverse of equivalence class 2, because 2 plus 4 is equal to 6, but that's 0 in Z6. So you kind of have to pay attention to the notation of whatever you happen to be playing with. Okay? Now, with that being said, we have our next theorem. And that is theorem 3.4. And 3.4 tells you this. Let R be a ring, and let A, B, and C be elements of R. And remember, in the ring structure, we're going to allow you to write this kind of stuff up. This little epsilon means elements of R. R is the ring. So A, B, and C are elements of R. If A plus B is equal to A plus C, then B equals C. Well, this is a very simple proof. So let's just go through it. And so we'll start off with the givens. You're given that R is a ring with A, B, C elements of R. Actually, I didn't actually have to state that. That's stated in the question. But this is needed. Also given that, if means given, A plus B equals A plus C. Well, as A is an element of R, because it's a ring, then negative A is an element of R, because R is a ring. And remember, in rings, the solution for A plus X equals 0 is going to be inside the ring, and that is that unique element, negative A. Okay. Thus, negative A plus B is equal to negative A plus A plus C. By adding negative A to both sides. Now, what's A plus negative A? That would be 0. Hence, 0 in R. A plus negative A is 0. Plus B is equal to negative A plus A is 0 in R. Plus C. By substitution. So that's all I did. I replaced the negative A plus A with 0. Therefore, 0 plus B is going to be B. B is equal to C. I'm going to state my reason there by the additive identity. Adding 0 to anybody makes it anybody. There you go. So again, it's very straightforward. You know, this is the canceling property in terms of addition. There's going to be something similar for multiplication, but that requires something special here. So here's your kind of your big theorem that really describes to us exactly what this negative A and is going to do for us, and some other properties as we threw them in here. So this is theorem 3.5 out of your textbook. It says this: for any elements A and B and R, we have this: A times 0 in R equals 0 in R is equal to 0 in R times A. And also remind you that 0 in R times 0 in R is 0 in R. So anytime you're multiplying the 0 element in a ring, you're going to get 0. But now let's talk about the properties of this new negative element here, the additive inverse. A times negative B is equal to negative A times B, which is equal to negative A element times the B element. So here's a little property for you about the negative. If one element is negative, when you multiply it times a positive, the whole thing's going to be negative. And it'll be the same thing as the first element was negative, multiplied times the second element, which is positive. Okay, so this elusive negative, referring to the additive inverse, can be moved around. Number 3 is pretty obvious to us who have ever played with integers, but we write it in terms of ring structure. The negative of negative A is equal to A. The additive inverse of the additive inverse of A is actually back to A again. That's, remember, that negative refers to the additive inverse. Okay? Here's the next one. the additive inverse of a plus b. The negative of a plus b is negative a plus negative b. And that's the same thing as negative a minus b, as we define minus as adding the negative. Similarly, the additive inverse of a minus b, when you distribute that additive inverse concept here, you get negative a plus b. And the last one is, if you take negative a times a negative b, that will be equal to the same thing as a times b. The additive inverse of a times the additive inverse of b is the same thing as just a times b. Now, what I want to focus on is this. Most folks screw this up very simply because they look at the wonderful world of negative as negative 1 times. And that's not necessarily the case. It depends on what kind of ring you have. If you got a ring with identity, it is. That negative represents negative 1 times. But if you don't have a ring with identity, there is no 1. So that negative refers to the additive inverse only, no negative 1 times. It has that property behind it, but you can't look at this negative as negative 1 times a plus b. It's just the additive inverse of it. Now, if R is a ring with identity, then the negative 1 in that ring, where 1 is the additive identity, negative 1 in the ring times a is going to be negative a. You can look at that negative as a negative 1 times, but only when you have a ring with identity can you do that. Otherwise, you have to look at it as the additive inverse element. So, and again, with this ring structure, we have other notations that we want to talk about. And there's 2 sets of those. The notation is, if A is an element of R, how would we write A times A times A times A times A times A times A? Now, there's 1, 2, 3, 4, 5, 6, 7 of these guys. We typically would write this as A to the 7th. Well, in ring structure, it's the same thing. The problem is that power. That power is not an element of the ring. That power is just how many elements you got multiplied together. So this is going to be your classic, integer, positive integer, countable number here. So we're going to define a to the n to be equal to a times a times a dot 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 times a n times, where just a is an element of the ring, and n is going to be some kind of positive integer of how many elements you have, which means you have your classic exponential properties from high school algebra, junior high school, whatever, still with you. This also means that a to the n times a to the m would be equal to a to the m plus m, and a to the m raised to the n is the same thing as a to the m times n. So the property of exponents still holds even when your base is an element of the ring. Now here's one that kind of frustrates some students, and logically so, but it's again trying to put in that algebraic structure from high school, and that is this. How would you write out a plus a plus a plus a plus a plus a plus a? We have 7 a's here, so that would be 7 times a in the good old days of Algebra 1 in the junior high school there. So it's 7 times a, but 7 is not an element of the ring. Only a is an element of the ring. A is an element of R. So again, we're going to make a definition here. The definition, we're going to define n times a, where n is that positive integer, and a is the element of the ring. So if you have n times a, that's the same thing as n plus n plus n plus n dot 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 plus n, n of them being added together. So n is a positive integer. Now, if you had the additive inverse of a being multiplied by n, the number of these guys, n times negative a, that would be negative a plus negative a plus negative a, n of those. And that's going to be the same thing as, you pull out that additive inverse aspect out front, that would be negative n times a. So we're trying to get that same structure that we had way back when in junior high school with the algebraic notation. Even with rings, that stuff still holds. Now here comes your big theorem. This is Theorem 3.6. This is going to be one you are going to memorize and use and abuse. We had Theorem 3.2. This is the new and improved version of it. Theorem 3.2, if you remember, was how you prove you have subring. But if you'll notice, I actually never proved anything with Theorem 3.2 in terms of subring. The Theorem 3.2 actually had to state that, quote, you had to have, let's see here, you got a subset S of a ring R such that it was closed. It was a zero element was in there. It was closed under addition, closed under multiplication, and you had to have the additive inverse of the equation a plus x is equal to 0 in R. Then the solution x equals the solution for x is actually inside the set S. Go back and look at the theorem 3.2. It's 4 properties that we happen to have to actually prove a subring. But once we define this concept of negative and subtraction, we can combine these guys. So let's take a look at this. This is your new and improved theorem 3.6. It says this: let S be a non-empty subset of a ring R, such that, number 1, S is closed under subtraction. What that means is if A and B are elements of S, then A minus B is an element of S. Remember, the minus is adding the additive inverse of B. Because if B is in S, negative B is going to be in S for free. Because S is going to be, a ring is going to be actually an R. So, but this idea of A plus negative B must be an S. And S is closed under multiplication. That means if A and B are an element of S, then A times B has got to be an element of S. So, 2 properties here. It says if it's closed under subtraction, as we've just defined subtraction, and closed under multiplication, then S is a subring of R. This theorem 3.6 is better than theorem 3.2 in proving subrings of a ring. Why is it better? Well, you got to prove less stuff. When I had theorem 3.2, you had to prove 4 things to be able to prove a subring. How many do I have to prove with theorem 3.6? 3 things. Yeah, I know, you're thinking 2, but no, there's 3 things. They threw an extra word at you, and that word is right up here. S has got to be a non-empty subset of a ring R. So, let me put it down here, and this is for our notes here, in terms of quoting theorem 3.6. Here's the big deal, the big star right here. Yeah. To prove S is a subring of R, 3 things you got to prove. Number 1, you got to prove the non-empty. How do you prove S is non-empty? What you do, the easiest element to show is going to be inside your set. If it even has a chance of being a subring, is show the 0 element of R is an element of S. If you show this, that makes it non-empty. There exists a dude inside S. So as long as you got one dude inside S, it's non-empty. So that's the first thing you got to do. And then the second thing you got to do is these 2 properties here. Then if you give yourself a couple elements, A and B elements of S, then you show that A minus B is an element of S. And then the third thing is, if, and I use the same guys, A and B are elements of S, and remember S has some kind of property, so it's that property preserving aspect you're going to be looking at. Then show that A times B is an element of S. And once you've shown these 3 things, then you can declare 3 dots. Therefore, S is a subring, and you just don't say it's a subring. You got to be being it's a sub. You got to be a sub of somebody else. So S is a subring of the overring R. R is the big ring. S is a subring of R. So this is actually by theorem 3.6. But still, 3 is better than 4. So this is a much stronger theorem, and this is the theorem we're typically going to use to actually prove you actually have a subset is going to be a subring. But before we get into some of those proofs, more definitions. And again, we've talked about these definitions before, and we're just rehashing them again. Now, we talked about these definitions when we were looking at the wonderful world of Z mod N, And that was an interesting kind of ring. It was basically called a finite ring, whether it was Z mod prime or Z mod n. We had certain definitions, and we're going to go back and look at them in terms of general ring structure. The first definition is this. An element A in a ring R is a zero divisor, classic zero divisor, if A does not equal 0 in R, and there exists a B element of R, got to be from R, with B also not equal to 0 in R, and A times B does equal 0 R, or B times A equals 0 R. The product has to be equal to 0. You got two non-zero elements multiplied together that gives you 0. Those are called zero divisors. A is a zero divisor, also B is a zero divisor. So zero divisors are non-zero elements that multiply by another non-zero element that gives you the 0 element inside of a ring. The other definition that we're going to rehash again and talk about in terms of general ring structure here is the concept of a unit, a multiplicative inverse. An element A in a ring with identity, you gotta have a ring with identity, R, is called a unit if there exists an element U in R such that A times U is equal to 1 in R, which is equal to U times A. Now here, it's commutative. Up here, when I was talking about just general rings, I never said anything about it had to be commutative. Now, I'm not talking about the entire ring being commutative, just the invertible elements are going to be commutative. If U is the multiplicative inverse of A times U is going to be 1, and it doesn't matter what side you put it on, U times A will also be equal to 1. That's a nice property of units. They will always, it doesn't matter what side you put it on, AU or UA, it's still going to cancel and give you the 1 element. Because remember, we have a ring with identity, so the 1 element is inside that ring. In this case, the element U is called the multiplicative inverse, sometimes it's called inverse, of A, and we got to do that math notation here, and it's denoted by A with that little -1, that classic A inverse. So typically, we can call them U if you want to, but A inverse, so the A inverse times A will give you 1. A inverse times A equals A times A inverse gives you 1. Okay. With this, we have to have a little bit more structure. So let's talk about this cancellation property again, but with this time, this cancellation property with the idea of multiplication. So this is Theorem 3.7. Theorem 3.7 says this: cancellation is valid in any integral domain. Now that's right out of the textbook. So let me write it up as a theorem. If R is an integral domain, and A, B, and C are elements of that R with A not equal to 0 in R, and A times B is equal to A times C, then B equals C. Now, again, if you go back and look at your definitions, well, if you've got the equation AB equals AC, well, then just divide by A on both sides. Well, one, we got rings. You don't divide anything. Well, multiply by A inverse then. That would be awesome if you had a field. A field is an integral domain where all non-zero elements are units. That's your definition of a field. I don't have a field. I just have an integral domain. So I don't know if A inverse exists or not. Remember, the definition of integral domain was that it was a commutative ring with identity, but no zero divisor. So anytime I got a product of two elements equal to 0, either the first guy's got to be 0 or the second guy's got to be 0. That classic zero property. That's what an integral domain has. Non-zero elements multiplied together will never be equal to 0. They've got to be non-zero. So anytime I have a product of two elements together equals 0, either the first guy was 0 or the second guy 0. That's an integral domain. But we don't have anything about units here. But here's the trick. Okay? So, as we look at this guy, let's take a look here. The proof. Always state your given. Given R, ring R, is an integral domain with A, B, and C be elements of R, and A is not equal to 0. also given that A times B is equal to A times C. Now I'm going to put this little paragraph form here. Then A times B minus A times C would be equal to the zero element R. And what did you do to go from this step to this step? By subtraction, which is perfectly legal in ring now, by subtracting AC from both sides. So if I subtract AC from the left and right, AC minus AC is 0. AB minus AC is what we have over here on the left. And remember, we're in rings. And so we got all those wonderful 8 properties of rings. Hence, what do we have in common? AB minus AC. When you have terms being added or subtracted, and you can they have a common element, then you could factor out that common element. So that's also the distributive property. So it'll be A times B minus C is equal to 0 and R. That officially is by factoring, but the fancy word for factoring is the distribution property. But remember, with distribution, just moving parentheses around, that's associativity. You actually have to factor something out of, you got 2 terms being added or subtracted, and pulling that element out of both terms. That's the idea of the factoring or distribution property. But since R is an integral domain, and A, the first element, is not equal to 0. In an integral domain, if I ever have a product of 2 elements equal to 0, either the first guy is equal to 0 or the second guy is equal to 0. But the first guy, A, is not equal to 0. Therefore, the B minus C, the second element, must be equal to 0. And this doesn't work in a general ring, but in an integral domain it does. An integral domain doesn't have 0 divisors. An integral domain, by definition, is a commuted ring with identity with no 0 divisors. No 0 divisor means anytime I have a product equal to 0, either the first guy is equal to 0 or the second guy is equal to 0. Hence, or thus, B is equal to C by adding C to both sides. And we're done. Now, as I'm going over this particular section 3.2, and I went over 3.1, even before you had your first test. Now, you guys are still studying for your first test and stuff like that. In the first chapter 1 and chapter 2, we focused on integers. And so, let Z be an integer, or Z mod n, integers mod something or other. So you have these elements in these guys. And so when you need to create their definition divides, A divides B. Well, by definition divides, there exists an integer x such that B equals AX. But now you've got to get rid of that notation of it having to be an integer. Now it's got to be an element of the ring R. So it's going to be the same idea. If R is a ring, and A divides B, then there exists an element x in R such that B equals AX. Don't say integers anymore. Say it's an element of the ring. So this idea of switching from the world of integers to the world of elements of a ring. So that's kind of what we're looking at, but looking at the structure and the properties of these sets called rings. Well, now, the next couple of theorems out of your textbook is honestly ones you look at and you go, well, that's pretty stupid. Yeah, but there's reasons for this and the way they state what they do. Look at this guy right here. Theorem 3.8 says this. Every field F, so now we're talking about fields. Remember what a field is. Every field F is an integral domain. And you look at this and go, yeah, by default. The definition of a field is it's an integral domain where all non-zero elements are units. Every non-zero element has a multiplicative inverse. Okay? So by definition, when you got a field, you're going to have an integral domain with an extra property. But the reason why they wrote this thing up there is sometimes you're trying to prove something is a field or it has some kind of special property. You don't need that multiplicative inverse. Maybe because you got an integral domain, you need that no zero divisor property, which fields also have. So this is the reason why they wrote it up as they did, but the proof is obvious, and even in the book they call it obvious. And you got theorem 3.9, and this was something interesting too, that every finite integral domain is actually going to be a field. So to be an integral domain that's not going to be a field, the integral domain has to be infinite. It's going to be an infinite number of elements. So if you go back and look at those z mod whatever, z mod n's, the guys that were actually integral domains that didn't have zero divisors were the z mod p's, z mod primes. But if you look at those z mod primes, because in a finite integral domain, z mod 7, the elements are 0 through 6, it's a finite number of them, that actually is going to be a field. Z mod prime is a field, so that because it's a finite integral domain, it's actually going to make it a field. All non-zero elements will actually have an inverse. It's a unit. Now, the rest of this lecture video is going to be focusing on proving subrings. As I mentioned right from the beginning when we talked about the concept of rings from chapter 3.1, I asked you the question, how many rings are out there? Well, of course, there's an infinite number of them. But where do I go and find these elusive rings out there? Well, sometimes once you've got one, instead of just trying to grab its straws out of the universe and trying to put them together and try to make rings out of it, once you've got an established ring, don't look outside, look inside. You'll be amazed how many subrings, which are rings of their own accord, but subrings are actually inside of a ring. And remember, Theorem 3.6 is how we're going to prove it. So I decided to grab a couple of these problems out of your textbook to help you focus on the proof of a ring. So here is problem number 8 in section 3.2 right out of your textbook. It says this: let R be a ring and let B be a fixed element in R. And let T be equal to, now here's the trick on this set notation that you guys are going to have to read. So let me show you how to read this stuff. Let T be equal to the set of RB, R times B, such that R is an element of R. In this set notation, this is what the elements look like. This is what property and where they come from. So this element, kind of what the property it has, this is what elements in T look like. And this is the structure that they have in it. So this T is an element of R, it equals to the elements RB, so it's R is an element of R. Remember, B was fixed. So, in English, here's the deal. T is all the elements that are multiples of B. So to be in T, you've got to be a multiple of B, where the first element came from R. That's the ring structure, or the set structure that we want. And we want to prove that T is a subring of R. Now, to prove a subring, again, we're going to quote Theorem 3.6. So let me go over Theorem 3.6 with you one more time. To be able to prove Theorem 3.6. Now, if you look at Theorem 3.6, it's worded accordingly. It's English here from a textbook. Let S be a non-empty subset of a ring R such that S is closed under subtraction, S is closed under multiplication, then S is a subring of R. That's awesome. Here's the real structure right here. This is what I want to focus on. To prove S is a subring of R, you got to show me three things. You got to show it's non-empty, and you do that by showing 0 as an element of S. You give yourself a couple of elements, A and B. So if A and B are elements S, I need to show you that that ring structure still holds over for S. A minus B is going to be inside of S. And with those same two guys, A and B elements of S, with that structure being inside of S, I need to show you that A times B is going to have that same structure. It's going to be inside of S. And once I got all three of these guys, I can therefore declare S is a subring of R. Theorem 3.6. So that's what I'm going to do here. All right, so proof. Always start with your givens. You were given. Okay, now. There we go. Given R is a ring and B is an element of R, a fixed element. Now what it means by that fixed thing, if that concerns you, R has a lot of elements. B is real special, like in Z207. 45 is real special. That's my element I'm focused on. 45 is that single element inside of R that I'm focused on. That's my fixed element. Okay? Okay, so that's just pretty much the givens. I want to show that this set T equal to R times B, that little line means such that R is an element of ring R, is this structure. I'm going to prove that that set T is going to be a subring of R. So the quote theorem 3.6, I first have to start with non-empty. Okay. Well, since 0 and R is an element of R, why? Because R is a ring. Okay. And as 0 and R times B is equal to 0 and R. I'm looking for that structure. And 0 times any element in R is going to be back equal to 0. Thus, 0R is an element of T, and T is non-empty. Now, right here is where people that take modern algebra before you start convulsing and freaking out and stuff like that. There's structure to this thing. First off, you got to read this structure here, and I'm going to do my little checklist. So I'm going to underline some stuff just to emphasize things for you guys. So T equals R times B such that R is an element of R. That's my ring structure. I want to show 0 is inside of T. To show 0 is inside of T, 0's got to look like this RB. Well, that's it. That's what I wrote down here. 0 in R is equal to 0 in R times B, where the coefficient in the front, the coefficient front 0R came from R. 0R is from R. It's because of this and this. These two sets of properties have been satisfied, which puts 0R element of T, and therefore T is non-empty. Okay? Now, that was part 1. So this is going to be a 3-paragraph type of proof here. So I'm going to put little paragraphs on these things. Okay? Now, the second thing you need to do, according to Theorem 3.6, is show closure under subtraction. But to show closure under subtraction, I got to give myself 2 elements. So here we go. I'm going to let my favorite 2 guys, X and Y, get an element of T. Now that it's non-empty, we know there exist some elements in there. I'm going to give myself a couple elements. And my favorite guys are X and Y. So let X and Y get an element of T. But T has structure. Therefore, there exists, now to be inside of T, you got to look like this, RB. So there exists an R, now this is where I go subscripts on this thing, R1 and an R2 element of R, right here, element of R, such that we have that structure, such that X is going to be equal to that first structure, R1 times B, and Y is equal to the other element, R2 times B. That's the structure to be inside of T. And it's got to look the exact same way, but I don't know what the coefficient element's going to be, so I call them R1 and R2, but they're all going to be times B, the multiples of B. Okay? I want to talk about closure under subtraction. Well, here we go. As X minus Y, there's my subtraction. This would be equal to R1 times B minus R2 times B by substitution. I just substituted them for X and Y, R1B and R2B. Substitution. Then X minus Y would be equal to R1 minus R2 times B by factoring. Factoring is a good word. Also, if you use the word distribution, I'm really happy with you knowing big words and stuff. So there it is, by factoring or distribution property. Okay. Now, we're going after this structure here. Now, I've almost got it. I got somebody times b in the back. That's what it looks like. But I need to also talk about why the guy in the front must come from R. Well, since R1 and R2 are elements of R, then R1 minus R2 is an element of R. Why? Because R is a ring. Property of rings. Rings have closure. We're trying to show this S, or this T element, is a subring of this guy. So R has that ring structure. So if I got two elements in there, their difference and their product is also going to be in there. Okay? And therefore, X minus Y is an element of T. Declare it. Now, again, I'm going to underline some stuff for you guys. Typically, you don't do this within the proof, but I'm trying to emphasize because some folks, after watching this awesome video that I'm making for you guys, are a little bit lost. Again, it's about this T structure. Let me show you that X minus Y has this T structure. Here it is. X minus Y is equal to somebody times B. So this first structure has been satisfied. And now the second part, which is the R, the guy in the front of the B, this second part has to be satisfied. And I satisfy that in my proof right there. So these two parts have been satisfied. That's what puts X minus Y inside of T. Now, here's the big deal. Catch a pattern on this stuff. So there's part one. I showed it was non-empty. Here was part two. I showed it was closed under subtraction. Part three is showed closure under multiplication. So I'm going to use the exact same two elements. So I'm not going to let them there be. We've already got them. I'm going to use them again. So instead of the word let, my third paragraph, I'm going to use the same guy. So I use as. And I restate it because, again, I'm going for that structure type thing here. I know it's overwriting this stuff and there are shortcut methods, but I don't want shortcut methods. I want to look for the three paragraphs that you're arguing, you're proving this thing is actually a subring here. So as X and Y are elements of T, therefore, I'm going to state it the exact same way. I am copying this guy. Therefore, there exists R1 and R2 elements of R such that X equals R1B and Y equals R2B. I'm recopying that exact same structure. But now, instead of showing the subtraction, I'm going to show the multiplication. So the other thing that I'm actually trying to show you here is the hard part on this thing is showing the closure and subtraction. Because once you got that, you're going to have to adjust. And it does a few definitions here. I'm going to adjust the subtraction to a multiplication and show you that. So here we go. So exactly the same. So there we go. As, now here we go. X instead of minus, I'm going to do times. As X, and you can use dots for times or just slap them beside each other, that's fine. As X times Y is equal to R1B times R2B by substitution. Okay. And then X minus Y, X times, replace minus with times, X times Y is equal to, now here comes my algebra here. Remember, to be inside of B, I want somebody in the front times B. Well, I've already got it. So it's not factoring. Factoring requires you to kind of pull something out over at addition or subtraction. Here, this is just moving parentheses there. X times Y equals R1B times R2 times B. All I did was move parentheses around. I didn't have to. There's no factoring. Don't call this factoring because it's all being multiplied. There's no, you know what you're factoring is the distribution property in reverse. There's no distributing this thing either. So, but what did I do? I moved parentheses. So state that by different operation here, associative property. Well, I'm going to show that I have the T structure here. So I've got the B in the back, so I just got to talk about the coefficient in front of the B. Well, since this time I got three letters, R1, B, which was my fixed element, and R2 are elements of R, then R1 times B times R2 is an element of R, because R is a ring. The closure of the multiplication of a ring. So again, I'm going to underline it. I got X times Y equals somebody times B, where that somebody came from R. Therefore, X times Y as the structure is an element of T. And then that last little bit I have up here, and I got damn much room to write him in. And another therefore, state your claim. Therefore, T is a subring of R by Theorem 3.6. All parts have been satisfied. So I have three parts of this thing. And the three parts are, I've got the non-empty part, I've got the closed under subtraction part of the x minus y, and I got the closed under multiplication part of the x times y. So all three parts have been satisfied. So therefore, by Theorem 3.6, S is a subring of R. So you have to declare what we're after. Remember, we were trying to prove T is a subring of R. So we're trying to prove that T is a subring of R, but declare your Theorem 3.6. That is your reasoning behind it, Theorem 3.6. So here's a great problem to study with the three parts. Also, you'll notice that my proofs are getting a little bit longer here in terms of being able to write these guys up. We're in Chapter 3, and remember, we're going through Chapter 6 because it's only going to get better for you guys. So I've decided to grab another problem. Great homework set. This was problem number 9 out of your textbook. Problem number 9 said this, and I just copied it right out of your textbook. Problem number 9 there. It says this. Show that the set of matrices, these are 2 by 2 matrices, of the forms, this is a special form here, of A, 4B, B, A, with A and B elements, that's a double backdoor, that's real numbers, is a subring of the set of M stands for matrices, where inside parentheses is where the elements come from, the real numbers of the 2 by 2 type. These are the 2 by 2 matrices. That 2 by 2 matrices is actually a ring. This format of the ring, A, 4A, B, and A, in this order, is going to be, that format is going to be a subring of the matrices. All right, well, I'm going to, anytime I hear the word prove somebody's a subring, automatically comes to my mind is Theorem 3.6. I got to show three things. Three things I got to show is number 1, non-empty. Number 2, closed under subtraction. Number 3, closed under multiplication. So let's see what we can do here. So, given, okay, M, R, 2 by 2 is a ring of, this is matrices, where the entries are real numbers of size 2 by 2, 2 rows, 2 columns. Okay. Then, who is a matrix? Now I'm trying to prove this thing is non-empty right off the bat. Then the matrix 0, 0, 0, 0 is an element of this M R 2 by 2. Okay. And as 0, 0, 0, 0 is actually equal to 0, 4 times 0, and 0, and 0. I'm trying to show you my structure here. The 0 matrix has that structure. 4 times 0 is 0 in real numbers here. Thus, 0, 0, 0, 0 is an element of, okay, we need to give this guy a name. Probably, but this is one I stole right out of the book. What's a good name for this guy? We'll call him n. Call him n equals. Is an element n. Always nice to give these guys a name. So it's of the n structure here. So I gave him a name. N is the structure of 2 by 2 matrices where you have A, 4B, B, A. Call that set n. So 0, 0, 0 is an element of that set n. It looks just like this guy. Thus, n is non-empty. You have to declare that. That's, you know, your check marks in terms of everything for Theorem 3.6 has been satisfied. Okay. The next thing I got to do is I got to show closure under subtraction. So I got to give myself a couple elements. So catch the pattern. Now, pick my two guys. But my favorite guys, x and y, be an element of this set n. But what does that mean? This means that there exists, I want different letters here. Let's talk about, let's see, we used A, B, so we'll do C, D, E, and F. That are real numbers, elements of the real numbers. Again, this is legal math jargon as you're writing up proofs now. You can use that element of the reals now. Okay, there exists a C, D, E, and F elements of real numbers such that I have the n structure such that x would be equal to, let's see, here's the structure, C, 4D, D, C, and y is equal to the structure, use the other letters, E, 4F, F, E. So I've got that same structure. That's what I'm going for here. Okay? As x minus y, closure under subtraction, what would that be equal to? That would be equal to C, 4D, D, C, minus E, 4F, F, E, by substitution. So we need an equation. You start on one side and just substitute it in, create yourself an equation here. That'll be helpful in your test later on too. Okay? Thus, x minus y is equal to, okay, and how do you subtract matrices? You subtract components. This would be equal to C minus E, 4D minus 4F, D minus F, and C minus E by subtraction. We are talking about a ring, you know, matrices, subtraction of matrices. Okay. And hence, x minus y, and I can factor out that 4. I'm left with C minus E, 4 times D minus F, D minus F, C minus E, by factoring distribution, if you will. Well, as C, D, E, and F are real numbers, then C minus E and D minus F is real number. So these guys make up real numbers. I have my structure. Therefore, x minus y is an element of that set n. This looks like the n structure, which was way up here. Okay? So, running out of room, so here's, and I'll just do this for your guys. Here's part 1. This is part 2, but I still got a part 3 structure to go for here. So I'm going to use a separate sheet of paper, but I'm going to pull this thing up here as I use my separate sheet of paper because I'm going to mimic the same routine here. Here it is. Okay. So I've got the x minus y. Now I want x times y. So I'm trying to put us all on the kind of same sheet of paper here. And so instead of let, we already got our elements. We'll just recall them again. As x and y are elements of n. Again, just recopy it. There exists a C, D, E, and F that are real numbers such that x was equal to the 4D, D, C, and y is equal to E, 4F, F, E. And I know a lot of students ask me, what do I have to recopy this thing over again? I'm using the same guys. Each paragraph should have that same structure to it. This is the closed under subtraction paragraph. This will be the closed under multiplication. Each paragraph should, quote, stand alone. Again, as you get heavier and higher level into senior level and graduate level mathematics, and we'll cut some corners on it, but not with your first math proof class. We're looking for that structure. All right, so pick it up right here. But instead of subtraction, we're going to do times, multiplication. So then things will change. As x times y is equal to C, 4D, D, C, times E, 4F, F, E, by substitution. Then, and now things are going to change, so I don't nearly need this sheet of paper right here. All right. Then, x times y. See, multiplying these matrices took up more paper on my little spot than I was anticipating. So, row by columns when you multiply. First row, first column. That's why Math 2164 was a prerequisite for this class. Remember how to multiply your matrices. So I'm going to put a big old bracket here for my matrix. It'll be C times E plus 4D times F. First row, first column. First row, first column match up. First row, second column. That would be C times 4F plus 4D times E. And I'm just trying to show you, I'm trying not to move my elements around and stuff. Second row, first column, D times E plus C times F, first row, second column, and then second row, second column, D times 4F plus C times E. Okay, by this time we're just matrix multiplication. Okay. So, let's take a look at this structure. Thus, x times y is equal to, let's see here, this is going to be CE, I'll use this structure, plus 4DF. Over here, I got a 4 in common, I can factor it out. It'll be 4 times CF plus DE. This one is going to be CF plus DE. I'm trying to make the elements look alike, so I did use commutativity on it, but remember these are real numbers, so that's a field, so no problems in commuting these guys. So they look alike. And now this guy I'm going to commute again. This would be CE plus 4DF. Look at your structure, and this is by, and I'll list all the things we did here, but it was just, you know, this is of the real numbers. You know, we did factoring, distribution property, if you will. You know, so let's see here. We also did commutativity. We moved some elements around. And factoring, commutative property of the real numbers. Okay. But look at their structure. Since we had here C, D, E, and F are real numbers, then CE plus 4DF and CF plus DE is real numbers, right? Okay, and that's a property of real numbers being a ring. It's actually a field. You just put parentheses field there. Okay, so he sums and products of elements of a field, or still elements of the field, because the field is a ring. So there you go. Okay. Thus, x times y. Look at the structure. The main diagonal is the same. The off diagonal, this is 4 times the element, and the upper component, the lower component, is the element itself. It has that ring structure. Thus, x times y is an element of n. And then the piece de resistance is the famous therefore. By, quote your favorite theorem, Theorem 3.6, n is a subring of M R 2x2, the 2x2 matrices where the elements come from the reals. Okay. So again, you'll see, especially if it depends on the structure of your ring, that these proofs can get, I'm going to be taking up a page because I started a half page out here. So here it is. So here comes the actual proof. So the proofs are a little bit longer. Now, as you're watching these videos, you should be taking some awesome notes with this thing. And the nice thing about the video versus the class is you can pause me and keep writing and then catch yourself back up and stuff. But it is a actual, you know, if you put it all together, it will take an entire page to actually write the stuff up. And maybe if I didn't write it so big and stuff. So there we go. Okay. And we got one more thing here, and I decided to pick up one more problem for you guys. And it's the famous prove or disprove. Now, in our world, we hate the prove or disprove because, you know, is it a prove or is it a disprove? You couldn't make up your mind? Well, no, I know what it is, but you need to know what it is. So the book likes to do this to you guys, prove or disprove. Now, on my test, because of the time structure, I try to make sure you guys get the test done within about 2 hours or whatever. I don't give you a prove or disprove. I'll either tell you to prove it, or I will tell you to disprove it with a counterexample. Well, this one is one of those thinking things. It says this: prove or disprove. The set of units in a ring with identity R. It's going to be a subring of R. So remember what the units are. So this is the idea. Is I'm going to create this set. We'll call it U. U is the elements A, it's element A, in R, such that A times B is equal to 1 in R for any B element of R. So for any B, so B is arbitrary now. So for any B, it's all the elements A that when I multiply it times that B, I get that 1 in R. That is the set of units. We want to show that U is a subring of R. But to be able to prove a subring, remember, you're going to quote Theorem 3.6. What is Theorem 3.6? Drum it into your head one more time. Theorem 3.6 is 3 things. Number 1, to prove it, you got to be non-empty. Non-empty set U. Number 2, you got to do closed under subtraction. And number 3, you got to do closed under multiplication. That's the way you think of Theorem 3.6 to prove actual subring. How do you prove non-empty? To prove non-empty, you've got to show the 0 element is going to be an element of U. Closed under subtraction, I'm going to use my favorite letters. Pretty much if X and Y are elements of U, then x minus y has to be an element of u. And then last, closed under multiplication, you got to do if x and y, same guys, are elements of u, then you've got to show me that x times y is an element of u. So remember the question. The question is this set, and I've kind of wrote them in set notation because that's typically how we're going to give these guys to you guys. The set of elements A from R, R's a ring now, the set of elements A from R says A times B is equal to 1 for any B in R. So you pick yourself a B, there's going to get this A and R, just their product is equal to 1. All right. First thing, so we think about proving it. Now this is all my scrap sheet of paper because I still don't know if it's a prove or disprove. Well, I look at number 1. Is this set non-empty? Remember, to show non-empty, the 0 element has to be inside the set. But here's your problem. 0 in R is an element of R because R is a ring with identity. It has that one element in there, but it's a ring. 0 in R is an element of R. But is 0 in R going to be an element of U? 0 in R times what element is going to be equal to that 1 in R? What element do I multiply 0 by to get 1? You don't. No x exists. Okay? So 0 in R is not going to be an element of U. So there's the trick right there. Since 0 in R is not an element of U, therefore this set U is not a subring of R. So now that's my scrap sheet of paper. I'm never supposed to show you this thing. So I'm going to answer prove or disprove. Well, to disprove this thing, since 0R is an element of R, and 0 in R must be in a subring of R. The 0 element's got to be on some side of you guys to see this. Since 0 in R is an element of R, and 0R must be in a subring of R, but 0 in R is not a unit, because you got to be non-zero to be a unit. The set of units is not a subring of R. There is my disproof statement. And then basically the counterexample, if you want to look at it from a, to disprove, you're going to come with a counterexample. The counterexample is the 0 element. So I did want to do that one. That was problem number 16 out of your book. So I grabbed a 3 problems out of your book because this is a great section, because you're going to do lots of prove something's a subring or type thing here. So Theorem 3.6 is going to be our key. So I hope this has been helpful. Study hard, take good notes off this stuff, and we'll see you on the next video.